maybe just a few words about Sweden. I thank the initial speaker for the map of Europe, and you saw Czech Republic, and above the Czech Republic there was a blob, quite large, but it has, and that's Sweden, is quite large on the map, but has very few people. We're only 10 million people, so roughly the same amount as in that small thing that was the Czech Republic. They are much more squeezed together than we are in Sweden, which is maybe why we are so happy, I don't know. Okay, so my talk will be on the supervisory control theory, which is a specific theoretical framework for doing a special type of control. We call it the classical AI approach, and I'm saying that it comes of age now because we have finally, after roughly 30 years of research, come to a point where we can actually use the results industrially. And I will show two examples of this. I will begin by presenting, give an outline of what supervisory control theory is and what we call the control of discrete event systems. I will describe briefly a tool that we have developed over many, many years, starting already with me as a PhD student. And then I will present two applications, current applications, of which I'm quite proud of, because they have shown that this theory and the framework is actually useful. The theory I will talk about is sometimes called the Ramage-Warner theory, which takes its name from the two inventors, you can say, Peter Ramage and Professor Warner. Well, Peter Ramage is also a professor nowadays, who developed this theory in Canada in the mid-80s, mid-late 80s. But the connection to artificial intelligence, well, according to a very famous book, which is named Artificial Intelligence, a Modern Approach, written by two very famous researchers, Russell and Orwig. AI, or artificial intelligence, was born in 1956, and that appears to be the first time when the term artificial intelligence was actually used. And it was in relation to Dartmouth's summer research project on artificial intelligence. That was the title of a get-together. A whole bunch of researchers who dealt with various topics such as automata theory, neural nets, and general study of intelligence. It had a very computer science theoretic view at that time. And automata theory, I will briefly explain what automata is in a few slides, was then mainly used for natural language processing. So there's this famous researcher, Noam Chomsky, who developed or used automata to describe, to model natural languages. There is a famous paper by Chomsky called Three Models of Natural Languages, where he basically shows that automata, as we define it here, cannot really be used to capture all of the intricacies of natural language, which is quite understandable. The important point here is that today automata theory underpins a specific field of control theory, the one that we call control of the discrete event systems. I will not show any equations. I will explain things by example or examples. So here we have a production facility. We have a bunch of input buffers on the top there, and an output buffer down to your right there. There are machining workstations, which are the larger blocks there, and there are automatically guided vehicles that travel around there, servicing the buffers and the machines and so on. And we see that there are, in the middle there are zone 1, zone 2, etc. And those are places where we can only have at most one of these automatically running transport units at a time. So what we need to do is we need to control the system so that these AGVs, automatically guided vehicles, do not collide with each other. Complicating factor is that we can only stop them at the red squares. The red squares. So we have red squares in these positions here. Thank you. So we have these red squares at these positions here. Those are the ones where we can stop the machines from entering these zones. And at these other squares, the gray squares, we can only observe that they pass by. This is an important and complicating issue when we're doing control. There are always some places where we can start. Let's look at a specific example, namely the lowest one, what we call sequence 5. And again, let me point here. So here we have a model, which is a state machine or an automata. It models this sequence here, and we can see the abstraction here, where we have these circles which represent positions along the track, and we have the transitions here, which represents where we actually can observe something happening. So as the AGV moves along, you can imagine that the active state actually changes there. And these states, there are situations where certain properties hold, like waiting to enter zone 4. This is given by Q9, which we have here. And then we have events, which represent significant occurrences, like exiting zone 4, which is U51, which is here. So this represents that we are inside zone 4, here we are now outside, and this represents that we leave. Simple models, quite straightforward, can be described mathematically. So we can do this for each of the components that we have there. We can have one model for each component, as I said, each AGV, each workstation, each input and output buffer, 12 components. And this will then be what we call a plan that describes everything that can happen, including having several AGVs in a zone at a time. This can happen, we want to avoid it, but in the description of how our world looks, it can definitely happen. Now we can compose these components, these different small models, into a big model by a specific composition mechanism that we call synchronization. Same events occur simultaneously or not at all. Sorry about that. In addition to a description of what can happen, we need a description of what we want to do. So the plan describes everything that can happen, including bad behavior, which these are the two bad behaviors that we have. And we need some way to specify that we must avoid these two bad things. We can have only one AGV in each zone at a time, and we can have at most one of these AGVs at the buffer at a time. So if you look at zone 4, to see how these specifications look, they have a quite nice star-shaped form. We have states, just as the other models. In this state, the zone is free. When an AGV enters, it goes to one of these states. Say C9 occurs, which means that the AGV enters from the left, goes into the zone. Then the zone is occupied until that AGV has exited with U52 down. And then we go back, and the zone is free again. Simple models, straightforward. I guess everyone understands that. You don't even have to be an engineer. What we now want to do is to calculate the supervisor, a controller, which can observe these happenings as the AGVs enter and exit the zones. And we want this supervisor to influence the plant so that we have a closed loop system, like what we see over there, where the supervisor stops bad things from happening to avoid that we violate the specification. And in addition, we want to restrict this model or system as little as absolutely necessary. I will skip so there are some technicalities here that maybe are not so important at this point, but to repeat We have a specification that describes the behavior of how we want the control system to look. I've already basically talked about the undesired behavior. We can describe the desired behavior. Also, we have some complicating factors that we need to take care of. But we know how to do those. I will only focus a bit on the last one there, so let me skip over quickly. One of these complicated factors called controllability has to do with the fact that we can only stop the AGVs at certain points and not at others. We can only stop them at the red squares. Non-blocking has to do with the fact that we always want to be able to return to some specific states, typically the initial state. If we look now what goes on here, we look again at specification 4, and if we put together models for specification for sequence 4 and sequence 5 and the specification for zone 4, we get a huge model only for these 3 components. Remember, we have 12 components, and this describes what goes on, namely that the system blows up into a big problem that we will see shortly. But first, let me quickly go through what we call synthesis, namely how to calculate this controller that we've been talking about. And I will only do this for a very small part of the system. So we look at only, again, zone 4 and a few of those events there. So if you compose and remove all of the other stuff that we saw in the previous picture that are not relevant here, we will get the system which describes a small part of the whole thing. We see that we have some crossover states here, and those are states that break the requirements or the specifications. We need to avoid those, and we can simply remove them in this particular case, because removing them does not create new problematic states. In general, it does, and so we have to iterate this process again and again and again. So this is then the result for this particular zone, to guarantee that there is only at most one ATV in that zone at a time when we look at just a small surroundings. Now here is the problem. There is a state space explosion problem. When we explicitly represent all these models and their composition, things blow up. You see in the table here, for the automatically guided vehicle, we have 10 to the power of 7 states. For other examples, a model of wafer processing, for instance, is very famous within our community. It has 10 to the power of 14 states. And of course, managing this within a computer is intractable. So, we need clever ways to fight this state space explosion problem. This is where our work comes in. So we have, over the years, defined and implemented approaches to actually fight this state space explosion problem by what is typically called divide and conquer. So we put the pieces together iteratively, and we calculate controllers, like what I showed before, for smaller pieces of the system, in such a way that when we're done, we can put it all together to control the actual big system. And this is work done with my previous PhD student, who is now an assistant professor with us, and a colleague of mine, Robin Halleck, in New Zealand. What underlies the possibility is that we can, there are always, or typically there are redundant information, redundant states in these models. And we can use automata theoretic approaches, borrowed from computer science, to actually generate smaller models. So we can have a model that looks like this, and we can observe that from this state and from this state we reach this state, and we have the same event. Then we can merge those into that one. Doesn't look like much, but and this is another way to do the same thing. Let me skip that. Doesn't look like much, but it has big consequences. It means that we can easily calculate supervisors for systems that have huge state spaces. Remember, for this model, we talked about 10 to the power of 14, and now instead we are talking about 19 different supervisors, the largest of which has 375 states. And this is what actually helps us in using this approach for practical problems. We have a tool which is available free for download and research, Java-based. We have a web page for it where you can download. So, now I'm going to go quickly through two examples of where these things have been used. One is in the application of control for Dutch water locks. So this is work by a PhD student who has recently graduated from Eindhoven University. And he will be a postdoc with me now this year. So in the Netherlands, the Rijkswaterstaat, which is the Directorate General for Public Works and Water Management, very old company, or the directorate, they are dealing with 128 water locks and 330 bridges, many of which need to be renovated in the foreseeable future. And renovated means implementing controllers for these. So the water locks look like this. Boats come in, the water is filled up so they can get up. Doors are of course shut, and the water is filled in, and then the boat comes out and the doors open and so on. So we have here a bunch of entering lights. In this case, 1 and 2, we have leaving lights, those are red and green lights, which allow the boat to go in and out. We have sensors for the doors, actuators to be able to open and close, sewer actuators and sensors to get in water and release water, equal water sensors, a whole bunch of other sensors, but that's enough for you to get the point at all. And look, most of these plant components can be described by very simple two-state finite state machines. So this one is the actuator for the upstream door. It can be off, meaning the door is closed. It can be on, meaning the door is open, and it can go off again. And then we have sensors for the downstream door, which tells us whether it's open or closed. And we can compose these into a model like the one on the right there. Now, the important thing here is that when engineers work with these systems, they write requirements of the type: the door, upstream door, on, requires or needs that the downstream door is not on. So I open the upstream door only if the downstream door is closed. That's what we're saying here. And this is the way they work. The engineers, they do this today. What's good for us is that this can easily be translated into requirements of this form, which basically says that, yeah, if we are here, then we allow the opening of the upstream door, but when we are over there, which means that the downstream sensor is on, then we do not allow the opening of the upstream door. But when the sensor goes off again, we now can again allow the opening of the upstream door. And for these use systems, and it looks like this. So basically, we have that model of the down door and sensor, and we have this requirement specification, and the synthesis will simply remove one of those transitions there that is not compatible with opening the door. Now, engineers do not really create these type of plant models. And for them to do that, we have to convince them of the benefit. In this simple example, we have only 14 of these two-state automata, so there are only 2 to the power of 14 states. And of course, that's somehow manageable by a human, but in the real example, there are 30 requirements, and almost all of them are toasted. But only even then, we reach already now 2 to the power of 30 global states, which is basically unmanageable manually. Yeah. So that was one of the examples, and I hope I'm having time I have time to go through the next one. So Sweden is famous for Volvo, which is not so much Swedish anymore, but still. And Volvo is working very hard on self-driving cars, autonomous cars. And they have set up a company called Zenuity, which does all the research and all the implementation of self-driving there. It's a spin-off company from Volvo and other company, implementing autonomous driving and advanced driver assistance systems. And we did a job there, or we had a multiple thesis project there on applications of formal verifications to the lane change market. Now, lane change is if you look at what Zenuity does, to put this into perspective. So if we can view the car as a cyber-physical system, and it has inputs, which is given by sensors and sensor fusion. Here we have traditional learning, deep learning, train nets, stuff like that. We have actuators, which is the steering and braking and etc. In between there we have the decision and control. And of course, if you have a self-driving car, you really want to know that the decision and control is correct, and that's what you expect of it. And this is where we now come in. We took a piece of the code that has to do with changing the lane. It's a MATLAB code. We modeled it in our tool, in similar models to what I already showed. We came up with a specification of a certain thing that we expected to be fulfilled, and then we did let our tool do the composition and verification, meaning that they tried to assess whether this specification was fulfilled or not. So if you look briefly at the lateral state manager, which is a system that handles lane changes, this sort of mimics human behavior. I know the Swedish traffic is not as complex, should we say, as here, but I still think that much of this goes on. There are additional things that is done here which we typically do not do in Sweden when we change a lane. We just don't honk the horn, for instance. But there is a point here called show intention, which could include these type of things as well. This is in the code, a state machine of similar type that we have here, or that I showed before, that keeps track of where in the sequence of changing lane that we are. So my students modeled this in our tool. We had a system. Basically, they do not manually write 1,400,000 states, but they put together a certain. They include some variables and a bunch of smaller component models, which together model this kind of state space. And of course, again, for a human to manually think through all of these 1,400,000 states and consider what should I do in this particular state and what should happen here and what should happen. That's totally impossible, right? This is just a brief outline of the model. You don't see much of that. So maybe it's not simple. But, so we put out this specification, and the specification quite naturally say that, okay, if I indicate to left, then I eventually should end up in the left lane. Sounds reasonable, right? This one can be described in this particular way. There are some variables in the code that we we can use to compare, and we check if this actually happens or not. And to much surprise, the answer is no. If you indicate to the left, it's not always the case that the car ends up in the left lane. Okay? Volvo engineers said, yeah, that's okay, that's fine, because we can indicate to the left and then we can change around and go straight. Yeah? But sometimes this code, existing code, can indicate to the left and then actually eventually turn to the right. And that's a big no-no, right? Our software tool found that, looking in a system of almost 3 million states, of which 1 million were bad. It took less than a second to find this problem, and we could show to the Volvo engineers that this problem actually exists in their code, which was again a big revelation to the engineers, and they said, oops, let's fix that. Yeah, so this is what I wanted to say. If requested to change, when the state machine is in a very specific state, then the car may turn to the wrong side. And this has a big, extremely complex sequence of several things which are very counterintuitive to each other, but was actually in the code. So, to conclude this, automata theory and finite state machines are useful as modeling for formalism for many engineering systems. I have shown 2 examples. We have lots of other examples also. We can now use them for verification and synthesis, for telling whether parts of some implementation works according to specification or not, or actually generate controllers that make the system work according to specification for industrially interesting applications. So we can treat systems of industrially interesting sizes. The computational complexity problem is not solved because it is inherently NP-hard, so you can always find examples where things go out of hand and you cannot do anything. But we have managed to push the limit of what we actually can do to be able to cover industrially interesting examples. The benefit is confidence in the correctness of the result of the thing that you implement, the engineers implement. 2 main difficulties remain. As I mentioned, engineers do not really model in this way, and that's one thing that we're working on now, taking existing models, like what we did with the code, MATLAB models, to automatically transform them into models useful for our tool. And specifications. This was an unanticipated problem. The engineers don't really know what the specs are. This thing that the lane change should always be to the indicated side, that was never written down anywhere. And maybe, or probably that was the reason why it was not implemented correctly. We don't know.